Good morning, ladies and gentlemen. I'm Jianjun Yu from JTE Corporation. Thank the organization for invitation here. My talk's title is Advanced Digital Signal Processing for High-Speed Spectrum Efficiency Coherent System. Here's the outlines for my talk. First, I give you a background and introduction about the DSP principle and motivations for our work here. And then I will show you 3 advanced DSP algorithms. Finally, give you conclusions. As you know, for 40G, I started the research and it's about 2000 year. But about 6 years, 440G is deployed. For 100 gigabit, this one is based on the coherent detection using DSP. Started the research is late 2006 and early 2007. Deployed in late of 2009. So just 3 years later, this 100G is deployed. So after 100G, 400G or 1 terabit is the next bit rate. This is the bit rate people started the research in 2010. And it should be deployed very fast. As you see, in order to increase the spectrum efficiency, we can use the high-order modulation format, such as 16 quant, 64 quant, even high. But if you're using the high-level modulation format, you need a much more OSNR. So the transmission distance will be reduced. Also, using this kind of high-order modulation, the DSP signal processing will be more complex and also need a much larger power consumption. Using QPSK, we can get a very basic trade-off between the spectrum efficiency and the transmission distance. In fact, this kind of modulation format is usually for 100 gigabit system. Is it possible or not possible to use this modulation for 400G or not? In fact, we find that we can use the advanced DSP signal precision to get this 400G with relatively high spectrum efficiency. And they have 2 modulation schemes to increase the spectrum efficiency. One called the next double diamond, another one called the optical wolf diamond signal. For all wolf diamond signals, they have multi sub-channels. Each one is a scanner. For double diamond, next double diamond, we use the strong optical electric field to generate the sharpening field. So you see, each sub-channel almost no crosstalk. But for the wolf diamond signal, when you detect this signal, you have to detect all sub-channels. So this one, you need a very large ADC bandwidth, and also the sample rate is very high. But for a next signal, since each time we just detect one sub-channel, so this sub-channel, the baud rate is close to the bandwidth. So this bandwidth is quite lower. So in this system, we do not need using the very high bandwidth ADC, and the sample rate also is lower. So next double diamond natively is a good solution in current situations, especially when the ADC or DSA bandwidth is limitation. Using the optical filter is quite easy to generate the next signal. Usually, we generate all the sub-channels and even sub-channels, and using the WSS, means wavelength selective switching, or even though using the optical interleaver, we can combine together. You can see this is the original signal, roughly the optical filter, so we get a much nano signal, and in this way, we generate the next double diamond signal. If you're using the negative DSP processing, we'll meet another problem. After the optical filter, the signal should be very nano. But for negative DSP, as CMMA means constant modulus algorithm, their frequency, the high frequency is enhanced. So in double diamond system, this crosstalk will be quite large. So in the receiver center, we can use the electrical digital pulse filter to filter this signal and get the signal nano. In this way, we can reduce the crosstalk and then we can use the following the MLC to reduce the BER. Here I give you an example. If in the using the regular DSP single polarization, in this system, the BER, the base BER just 3 times minus 2. So you can say even though in CD generation FEC limitation, you still can get error free. But if using the new advanced module DSP, we can get the BER much narrow, much small. And this one show you how to convert the 2-level signal to 3-level signal by using the digital filter. You can see this is the QPSK signal. This is I, and after 1 bit delay, and we add it together, so we generate 3-level. This is for I, and here's for Q, so we can also generate 3-level signal. So if for QPSK, we by this procession, then we generate the 9-core signal. So by this way, generate 9-core signal. So for this kind of, So first, I introduced the first DSP algorithm. This one called using the post filter. You can see this one is similar to the regular DSP procession. First, we're using the electrical domain CD composition, kinematical dissipation composition, and we're using the CMMA to separate the 2 polarization, because we transmitted the signal is 2 polarization, is double polarization. So we're using this one to separate the signal, and then we're using this regular frequency offset equalization to compensate the frequency offset, and then using the β p phase recovery to get the phase equalization. So you can see all single procession based on QPSK, but we're using the post filter to generate the 9-core, and then using MLC to reduce the BER. This is the experiment we're using this algorithm. You can see we have transmitted a 1.6 terabit next double signal. They have the 80 channel. Each channel is 200 gigabit. We're using the WSs combined together, and then transmission fiber is the field fiber, and this is a coherent detection. And here is the optical spectrum. This is the optical carrier separation signal. After the strong filtering, we can get the much nano, and we meet the BER. We can find by using this algorithm for a single channel or double dimension channel, their penalty is smaller than 1 dB. This is the transmission fiber. In fact, this experiment was done with joined the experiment with Deutsche Telekom, and this is their research center. We transmitted 10 nodes. Each node the distance from 30 to 70, 80 kilometers. But the average loss per each span is about 21 dB. And this field fiber, the distance is roughly about 900 kilometer fiber. So we put it on 800 real fiber in their another research center. So the total transmission distance is about 700 kilometer fibers. And another DSP, we usually call it multi-modulus equalization based on CMMA. This one you can see is different from the first one. And this one we boost the multi-modulus. You can see after the strong filter, the signal should have 3 levels. So you can see this one have the 3 levels. This is the middle one, and this is the second ring and the third ring. And then we're using the force power equalization to get to remove the frequency offset, and then using the modified β p to recover the signal, and then using the MLC to reduce the BER, and finally we get the BER results. You can see this one have good. We can get better results. The reason is, for example, this one using this is the original signal. If we using the CMMA, regular CMMA, the spectrum will be enhanced, so the crosstalk will be large. But if your signal is recovered by 9-core, So you can see the spectrum at high frequency not enhanced, in fact, it's reduced. So in double diamond system, the crosstalk will be small. So using this DSP, we can reduce the RSI and maintain the high performance. But for this kind of signal, we need to do some special singular processing for frequency offset or for the phase recovery. You can see this one to have the processing to have 3 steps. First, we need to partition the 3 lanes. So this one is 0, 1, and the other 1, and the other 2 and 3. Yeah, they have the 3 levels. And we need to rotation the other 2 to I quad pi, and then we equalize the other 2 and other 3 signal, and then get the QPSK signal. This one is quite similar to QPSK. Then we can use the standard QPSK DSP to do the signal processing. So before do that, we need to do some special processing. Here is the process. And by the way, just as I mentioned in the last slides, yeah, we need to do normalization for R3, and need to rotation and normalize for R2, and then we need to use the standard DSP signal processing for QPSK to do the frequency offset equalization and the power equalization. This is based on beta B scheme. And we get some results. You can see using this the CMMA plus post filter. This is the DSP1. The result is here. If we use the DSP2, we get 1 dB improvement. For the transmission distance, we can increase about 32% increase distance by using the DSP2. So we can get the transmission distance about 2,060-40 km fiber in the standard single mode fiber. The CD DSP we could using the decision directed least radius distance. But this one you can see is a little difference. This one we have the 2 loops, and the first one we using the regular CMMA and to do pre-equalization, and then using the regular frequency offset to estimation to get this the frequency offset, and send this offset to the second loop. In second loop, we're using the DD-LRD to do single processing for this physical recovery, and then using the regular frequency offset and the phase recovery to recover the data. So this one is a little different than the first one, and by this scheme, we also can get good results. And using this one, we also can use it for the 16 quant or even high quant signal, not just for QPSK. Here is one experiment by using this DSP. You can see we have 16 channels. Each channel modulated 6 gigabaud IQ data. So, and then position multiplication. So each one is 240 gigabit. So we combine the 2 sub-channels together, get 480 gigabit. And we're using the WACS to generate the next signal, and then transmission in this loop. You can see this loop is they have the 100 GHz wavelength select switch. We're using this one simulated 100 GHz bandwidth. And you can see the transmission distance, the loop transmission is 200 km fiber, and each one, each span is 50 km. Using all llama, and this DSP single processing, we're using the DSP3. We compare the different bandwidths. WACS, it is a different bandwidth. We can find the power penalty almost is very small when the bandwidth is larger than 38.5 gigahertz. 38.5 gigahertz. And even though using the 66 gigahertz, the power penalty is just 0.5. You need to remember, this signal is a 60 gigabaud signal. So pass 3, 66.6 gigahertz, still low, almost low power penalty. So we can get a very high spectrum efficiency. And this one is a transmission distance. You can see this one is this result is with loading, and this one is without loading. You can see their difference is not so large. So this can send after using over DSP, we can transmission about 5,000 kilometer fiber, 5,000 kilometer, and they transmitting 25 nodes. And here is the DER results. We measure all channels, so we get so all channels can transmission 5,000 kilometer fiber. Spectrum efficiency is 4 bit per second per hertz, and they can transmit 25 nodes. So here's the conclusions here. You can see using advanced DSP, we can largely extend the transmission distance. And here we introduced the 3 DSP. Each DSP have a different performance. This one is quite simple, but the performance is not as so good as this one. But the DDLRD is relatively complex, but it can be used for the 16 QAM or even higher order level QAM. And we have demonstrated the 8 channel, 400 gigabit signal transmission, 5,000 fiber, 25 nodes. In fact, this is the longest distance is this spectrum efficiency. Here's our publications on next double diamond transmission. We have the OFC PTP and a lot of journal papers. Thank you for your attention.
Okay, let's thank the speaker. Okay, let me allow a quick question before we go ahead with our program. Yes, please.
Distance is because you use shorter spans of fiber and you use Raman amplification. Can you comment on that?
You are right, yeah. In this case, for 5,000 kilometer fiber, we use Raman and the shorter span, but we're also using the long span 8 kilometer fiber, and using regular EDF we transmit 2,800 kilometer fiber. In fact, this one is also the longest transmission distance for this spectrum efficiency.